I really enjoy doing pump problems, so let's do 3 of them. This first one will pump water out of a pond, up a hill, and into a storage tank. A pump operating at steady state draws water from a reservoir and pumps it into a tank at an elevation 15 meters above the surface of the reservoir. The power input to the pump is 0.52 kilowatts. The water temperature remains nearly constant as it flows through the system, and there's no significant change in kinetic energy from inlet to exit. Heat transfer between the pump and its surroundings is negligible. Input conditions for the water are T1 is 15 degrees C, P1 equals 1 bar. Exit conditions are P2 equal 3 bar. Determine the mass flow rate of water in kilograms per second. Let the acceleration of gravity equal 9.81 meters per second squared. Let's lay out this problem. There's lots of parts to it. So we'll start with the schematic. We have a pump, and it has an inlet pipe that goes down below the surface of a pond. And it has a discharge pipe that goes up a hill and into a storage tank. The state 1 is going to be inside the inlet pipe right at the level of the surface of the water. So when the pump's not running, there'd be water inside this inlet pipe. It'd be at the same level as the water outside the pipe. And we'll call that elevation our datum and give it a value of 0. All right. State 2 is at the discharge of the piping system where it enters the tank. And we're told that there's no change in kinetic energy. So even though this drawing shows a larger inlet pipe than discharge pipe, we're going to assume that the diameters of these 2 pipes are identical, and that is why there is no change in kinetic energy. And of course, the elevation of state 2 is 15 meters above our datum. Now, we were told that the pressure at state 1 is 1 bar. Well, that's because we're taking the atmospheric pressure at 1 bar. So the pressure of water at the surface of the pond is 1 bar. And that's what we have at state 1. Now at state 2, if we were just discharging water out of the pipe into the atmosphere, it would also have a pressure of 1 bar, but that's not the situation here. It's pumping into a tank, and there's a head of water above the outlet of the pipe, and that head of water creates an additional pressure at state 2 for a total pressure of 3 bar. So let's see what we're given. We have the temperature at in the pond at the inlet of our system is 15 degrees C. The pressure at the inlet to our system is 1 bar, and the elevation is 0. And let's be sure to define this system as all of the water inside this pumping system between state 1 and 2. So it's the water from state 1 through the inlet pipe, through the pump, through the discharge pipe, and up to the tank. That water is our system, and that's what we're going to apply our equations to. Now at state 2, the temperature is basically the same. They said virtually the same. So we'll say that T2 is equal to T1. That's how we'll model that. And the pressure was given as 3 bar, as I mentioned. And the elevation of state 2 is 15 meters above our datum. We were told that there was no heat transfer into or out of the system. So Q prime will be 0. We were also given that the work or the power used by the pump is 0.52 kilowatts, which we have to put a negative sign in front of, because work is positive when the system does work on its environment. So if this pump were delivering work to the surroundings, then this would be a positive number. But we know that pumps consume power, and so it's negative 0.52 kilowatts. Let's see if we can visualize this on a TV diagram. So we've got a vapor dome, and we've got this water in our system is subcooled water. And there are 2 pressures. We have a pressure at state 1 of 1 bar, and a pressure at state 2 of 3 bars. So let's draw this 1 bar line in here, and it will then come down out here into the subcooled liquid region. The same for the 3 bar constant pressure line. It'll go under our vapor dome and then extend out into the subcooled liquid region. And both state 1 and state 2 are at 15 degrees C. So I've plotted state 1 at 15 degrees C on the 1 bar line, and I've plotted state 2 on our 3 bar line. And it would seem like they have two different specific volumes. But we know that's not true. They're at the same temperature and they're subcooled liquids. So V1 is going to be equal to V2, which is going to be the specific volume of a saturated liquid at the same temperature, which is 15 degrees C. So really, the reason it doesn't look right is because these constant pressure lines that extend out into the subcooled liquid region don't really stick out like this. This constant pressure line actually hugs the saturated liquid curve, the left side of the vapor dome. These lines don't really stick out here at all. You've got to remember that TV diagrams are really more schematic than they are drawing, and we put these pressure lines out here to help us visualize what's going on in most cases. But here it's a little distracting. So if we really extend these constant pressure lines right down the saturated liquid line, then P1 would be right on top of this saturated liquid line, and P2 would be also on top of that. So they're really, these two states are really right on top of each other, and they're virtually right on top of the saturated liquid line. So let's see how we're going to model this. It's going to be an open system operating at steady state. The change in kinetic energy was given as 0, and we'll assume that the diameter of the pipe is constant. We were also told there was no heat transfer into or out of the system. And as already mentioned, we're going to treat this as a subcooled liquid. And our chore is to find the mass flow rate in this problem. Well, to find the mass flow rate, we're going to use the energy balance. So we have, for these open systems operating at steady state, we know dEdt is 0. And we also know that that's equal to Q dot minus W dot plus M dot times the change in enthalpy plus the change in kinetic energy plus the change in potential energy. Now in this case, we were told that Q dot is 0 and that the change in kinetic energy was also 0. So we'll cross out those terms. And now we can simplify and rearrange. Let's solve for the mass flow rate. Well, M dot becomes the W dot divided by H1 minus H2 plus G times Z1 minus Z2. That is our potential energy term. So if we can find all of these values on the right side of the equation, we can calculate the mass flow rate. Let's start with H1 minus H2. How do we find the change in enthalpy for a process that involves subcooled liquids? Well, it's this equation here, which is a very important equation, and you'll want to keep this in the forefront of your notes. The delta H is just C delta T plus V delta P, where C is the specific heat of the liquid. Now, as you will recall with gases, we had two specific heats. We had C sub P and C sub V. But as the gases liquefy, C sub P becomes equal to C sub V, or it's just C. So liquids only have one specific heat. We'll call it C. And this is the expression for calculating delta H. So let's expand that. We have H1 minus H2. It's just the specific heat of the liquid times T1 minus T2. But in our case, T1 equals T2. So T1 minus T2 becomes 0. And that leaves only in this expression V delta P, or V times P1 minus P2. Well, we know the pressures, but we don't know the specific volume. So let's go to the saturated water table at 15 degrees C. And we know that the specific volume is very nearly the specific volume of a saturated liquid at the same temperature. And from the table, we get that to be 0.0010009 cubic meters per kilogram. So now we can write that H1 minus H2, we'll go back to this V delta P term here. It's the specific volume, which we just found in the table, times P1 minus P2, which is 1 bar minus 3 bar. And since we have units of bar cubic meters here, we'll write a unit conversion. 1 bar cubic meter is equivalent to 100 kilojoules. So now we can solve for H1 minus H2, or delta H. It's just minus 0.20018 kilojoules per kilogram. Now we have enough information to solve for the mass flow rate. It's the work or power term. It's minus 0.52 kilowatts, which we'll recall that a kilowatt is defined as a kilojoule per second. So I'm going to make that unit conversion. And then we're going to divide by H1 minus H2, which we calculated has this value here, minus 0.20018 kilojoules per kilogram. That's our delta H term. And then we have our change in potential energy, which is the acceleration of gravity, times Z1, which was at our datum of 0, minus Z2, which was at an elevation of 15 meters above the datum. And now we have meters squared per second squared. And as you recall from previous work that we've done, that 1,000 meters squared per second squared is equivalent to 1 kilojoule per kilogram. That'll get our units lined up, and we can conclude this calculation. The mass flow rate is 1.498 kilograms per second. And that's how we do that pump problem.